Alright, so in this video I'm going to take a look at a task I designed to revise Year 12 stuff before moving on to Year 13 SHM content. So we're going to look at some resolving vectors and look at integrating and taking the derivative of sine and cosine functions. Okay, so let's start off with some resolving and combining. So we've got a boxer launching a jab punch of 500 newtons at 30 degrees above the horizontal, so let's sketch that. That's the horizontal, so 30 degrees, and the force is 500 newtons. Calculate the horizontal and vertical components of that force. So these are your sides of the right angled triangle. So this one is going to be 500 sine 30, and this one is going to be 500 cosine 30. You can see that for yourself if you use some trigonometry. So the force in the vertical component was 500 sine 30. Sine 30 is a half, so that's going to be 250 newtons there, which strictly speaking we should write as 2.5 times 10 to the 2 newtons to give it to two significant figures. And the horizontal component is going to be cosine of 30, which is root 3 of 2, times 500, gives you 433.0 blah blah blah, which is roughly 4.3 times 10 to the 2 newtons there. Alright, so we've got our two components of the force. So let's move on to the next one. So a fencing athlete moves 1 meter north and 20 centimeters east. So that's 1 and 0.2. Calculate the magnitude and direction of the resulting displacement. So the displacement is going to be this, and we're going to want this angle in there. So S, using some Pythagoras, is going to be the square root of 1 plus 0.2 squared. So let's calculate that now. 1 squared plus 0.2 squared square rooted is 1.019 which is actually still 1 meter to 2 SF. Theta, we've got the opposite and the adjacent, so let's use a tan function. So the inverse tan of opposite, so 0.2 over the adjacent, so 1. 0.2 divided by 1, inverse tan, 11.3 yada yada yada, so approximately 11 degrees to two significant figures. Alright, so let's have a look at the next one. Let's make sure all of the bits move together. Okay, so the vertical position of a cyclist's feet can be modelled with the equation x, which will be the position, so the displacement is going to be given by sine of kt. So to differentiate sine kt with respect to t to generate equations for velocity and acceleration. So the first thing to know is that when you're taking the derivative, essentially it goes round in a loop like this. So we're going to go round this way, so taking the derivative round sine round to cos, and then whatever's multiplied by t would come outside of the function. So it's going to be k cosine, and then whatever's there stays in there, like that. And then acceleration, we're going to take the derivative again. So whatever's in comes outside, and cos goes to minus sine, so we're going to get minus k squared sine kt. And when you get into SHM, you'll see very quickly what k represents in your SHM equations, but this is the general version of it. Okay, so let's move on to the next set of questions. Okay, so what we need to do here is take this displacement versus time graph and we need to turn it into a velocity and an acceleration graph. So we can see in this first section here, the displacement isn't changing until 12 o'clock. So let's mark that on there. So the velocity graph is just going to be 0 up until that point there. Then what we can see is the velocity, it's traveling a certain distance. The gradient is constant, which means velocity is constant. So between 12 and 12:30, so let's mark on 12:30, you can see we've got a constant velocity. So let's call that this section up here. So we can see it's changed instantaneously. So you normally represent that with dashed lines just like this. We can see its velocity is going to be 100 kilometers an hour because it does 50 kilometers in half an hour. So this is actually 100 kilometers per hour. Then we've got its displacement not changing in, so its velocity goes back to 0 for the time being. Then the next section, you can see it does 50 kilometers in 1 hour, so it's going to be like this at a lower speed. Then we can see it's not moving in for a while, so we've got this section here, and then we can see its velocity is minus, and it changes from 100 kilometers in half an hour, so that's effectively minus 200 for this section here. So this is minus 200 down here, this is 50, and then we had this was 100 there. So that's the velocity time graph, and because it's all straight lines, the velocity is going to be constant during each section. So the acceleration graph, you see the velocity graph is horizontal, like the velocity is constant at each of the different locations. So acceleration is never actually changing, so what it is, it'll just be a flat line going across like this. Because velocity is always constant, it's instantaneously changing. So a bit of a strange one, but if you have instant acceleration, that's what it's going to look like. You could in theory argue that you've got kind of like spikes at like each of these times where it has that infinite acceleration, but let's not worry about that too much. Okay, so let's move. Alright, so let's move up to a higher difficulty level. So our punch in the first question is going to be followed by a second punch, and it wants to calculate the resultant of those two. So if we do the same as we did before, we essentially split it up into its components. This one being 400 sine 70, this one being 400 cosine 70. So when we think about calculating the overall horizontal component of the resultant, it's going to be the sum of the two horizontal ones. So it's going to be this one, so 400 cosine 70 plus the original one, which was 500 cosine 30. The vertical component of the resultant is going to be the sum of the two vertical components. Like this. And then to get our overall resultant, all we're going to do is add these, or use Pythagoras if you like. And when we put those numbers in, what we get is 8, 4, 9, blah, 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 blah. So it's approximately 8.5 times 10 to the 2 newtons there. Is going to be the resultant force when you combine it with the stuff we already calculated for question 1. Okay, so acceleration of a taekwondo strike is modeled using A equals sine 2t. If we want to get velocity, we will have to integrate that. So first we divide by whatever's inside the brackets multiplying by t. Sine, when you integrate it, would go to minus cosine. And then, so that's that one, and we've got 2t. And then to finish off, the acceleration will be integrating that again. get it like this. Now we were integrating between limits, so the change in velocity is going to be when we put those limits in. So when you put pi over 4 in there, you get cosine of pi over 2, which is 0. When you put in 0 in there, you get cosine of 0, so that's 1 times minus half, so minus a half. So it changes by 0.5 meters per second. Change in acceleration, put the values in. So if we put pi over 4 in there, we get sine of pi over 2, which is 1, so that's going to be minus a quarter, minus 0, which is what happens when you put 0 into sine. So the acceleration is actually going to decrease by 0.25 meters per second squared there. So these are our change in velocity and our change in acceleration. Okay, so let's scroll down and I'll zoom out a bit so we can see this. So during a rowing, the vertical position of an oar can be modelled with a sketch shown, which is kind of what you expect because it would go up and down. Calculate the corresponding velocity and acceleration graphs for the oar. Okay, so velocity is the gradient of your displacement graph. So displacement is initially flat, so your velocity is going to be initially 0. And when we go, I guess, like pi over 2, if you like, later on, we can see that the velocity is its maximum, but negative. So it would be down here. Then we go back to the center point, it's gone back to 0. Then it's at its maximum positive, back to 0, maximum negative, back to 0, maximum positive again. So we get something that looks a little bit like this. Not amazing, but perfectly. And we can see essentially that this one is always the gradient of the displacement graph there. Okay, so in terms of acceleration, we go through a similar kind of process. So initially, the gradient of your velocity graph is very negative down here. So if the gradient is negative, that means acceleration is negative. Gradient 0, gradient's very positive, gradient 0, gradient's very negative, gradient 0, gradient's very positive, gradient 0. So essentially, this is what the acceleration equivalent would look like there. And a key feature which will be important for SHM, we can see that this one here is like flipped in the x-axis with this one here. So they're actually pi radians out of phase of each other, or like just the minus graph of each other, reflection in the x-axis. So that will be important later in SHM. So I thought I'd point that out. All right, let's move on. All right, so this is the final part. So we've already had the person hit twice, and so the result of them being hit is they're actually going to leave the ground because it will give them a vertical component of velocity. So essentially what we're trying to work out is they're going to leave the ground with a certain velocity. What we need in terms of working out the air time is what the vertical component is, v sine theta. So sine of theta, so theta is going to be a similar triangle to the force one. So it was, I think it was 625 something divided by 846. So that will be your sine theta. That will just be from your force triangle. Remember, we had the resultant was 846. I think this was 625. This was like 569 point something, and then that's theta in there. So the velocity triangle would essentially match up with the force triangle there. Okay, so the change in momentum in the vertical direction is going to be calculated by force times time. So the vertical force was 625, and then times it by time, which was 0.1, and that will tell you the change in momentum in the vertical direction. So the velocity is going to be force times time divided by mass, which is 1.04 blah 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 blah. So that's the velocity in the vertical direction, or v sine theta, if you like. Now thinking about what its motion will look like. Essentially what it's going to do is go up like this, and the key feature here is that at the top its velocity is 0. So we're going to use that, and our Suvat equation, v equals u plus at. So 0 is going to be equal to whatever it started with minus g t over 2. Remember, it takes exactly half the time to get to the top. So if we put in our 1.04 divided by 9.81 gives you t over 2 multiplied by 2 gives you a total time of 0.21 seconds there. So just to recap this one, the first thing we've done is work out how much momentum the force has given it in the vertical direction. From the momentum, you got the vertical velocity, and from that velocity, we use Suvat essentially to calculate the time to halfway up in the air, and then from that worked out what the total time it would be airborne was.